Thanks everybody for joining. Today we're going to be talking about plastic welding integration for custom automation made easy. Before we get started, I want to just make sure everybody knows how to use the chat. So there's no chat messages yet. So somebody type something in the chat. Say hello, tell us where you're joining from, how's the weather, what's your favorite color, favorite flavor of ice cream, and also how many clouds are in the sky. Okay, I've got a hello from Catherine. Thank you. Nick said hello. He's in the room here, so he doesn't count. Jason Perkins, good morning. Good morning. Great. You know how to use it. You can type a question in there at any time. We will do our best to answer those as we go along. We are not going to wait until the end. We might say, oh, we're going to get to that. But for the most part, we're going to try to answer the questions as we go. Because if you're anything like me, if I have a question burning in my mind about something that's being said, I no longer hear anything else that's coming because I have the question and I need it answered. Right. So a little bit about Xtol. We're going to go through a little quick intro about Xtol, our approach to integration packages, and then we'll talk through how integration works for a bunch of different plastic welding technologies that we offer. All right. Xtol, we exist to solve complex plastic manufacturing challenges. If you take a look at our logo, it's sort of a cross, and that cross is a spectrum. On the left-hand side, there are companies that have plastic welding expertise, and on the right-hand side, there are companies with custom automation expertise. What we have found is plastic welding providers typically don't do very well with custom solutions. On the right-hand side, custom machine builders may need help with the plastic welding technology because they're not experts in that. Xtol is the best of both. Customers can get a configurable plastic welding solution that is optimized for performance. So what does that look like for machine builders?
Yeah, thanks, Jason. We create using decades of experience in plastic welding, plastic assembly, plastic staking, and we've developed technologies over the past, let's say, 15 plus years. So using that plastic experience, we have found that machine builders, integrators, automation houses, they excel really well at implementation of various technologies. I was at a customer's facility last week, and Xtol had done an automation hot plate welding system that coupled with the automation system. And this particular machine builder had probably, I'm going to guess, 9 different OEMs, 9 different pieces of technology. And they couldn't be experts in all of them. That's where we come in. So let's talk a little bit about what the specific areas of Xtol are and how they could apply to you and maybe your custom machine application or how you might want to implement our technologies. We offer engineering services where we're developing technologies. We're also developing customer parts. If you've got a customer that's not really sure what weld geometry they need, we do a lot of that work. We do prototype work and validation work. That has accelerated over the past, I would say, 5 to 10 years massively. The typical DDP&Rs we find don't exist like they used to. And so engineering services, we've got a group of application engineers, a couple innovation engineers that can help with that. The plastic technologies you're going to hear about in this webinar are InfraStake and nanoSTAKE, InfraGuide, which is an IR welding type of technology, laser welding, hot plate welding, spin welding, InfraWeld, 3D printing. We'll talk about how to apply that. And then we do some of our own custom automation. That's kind of what Jason was talking about. And we do that with fully automated systems, semi-automatic systems, standalone, and integration-specific packages that are really easy to use. So why use Xtol for integration packages? We've talked a little bit about the plastic experience and bringing that decades of plastic welding experience through a whole variety of technologies. I work with our laser plastic welding group, and I often say we don't just do one technology. If laser welding isn't the right thing, we won't suggest that. And some suppliers, that's what they'll do. Proven technology, you're not implementing it or integrating it or putting it on your machine for the first time. You know that it's going to work because we maybe even have run those parts in our applications lab. And then lastly, we, after offering tools and plastic technologies to integrators for the past 15 years, we really understood that an easy interface is required. So what does that mean? It needs to have a good mechanical interface where we've got engineers matching up your equipment maybe with our staking technologies or our welding technologies with a fruit conveyor or whatever the case might be. Wiring is really critical, making sure that you can just receive it, wire it up as the instructions state, and we'll give some detail to that in a minute, and you're ready to go. Controls, we've got a variety of different control solutions for machine builders. It might be a canned sort of template program where it's a drop and go. It might have a little bit more communication understanding, but we consider that in all of our integration packages, whichever solution might be. And then validation. This is really critical. I was talking to Jason as we were preparing for this webinar that one thing we try to do is, if we can, do an FAT, do a factory acceptance test here. We might be taking your lower nesting. We make sure that you're going to get the performance that you want before it's out in the field. Now, that's not the case necessarily with staking, because staking is a pretty straightforward solution, but for welding, that's what we try to do. So to see what this kind of looks like compared with our technologies and what we're going to talk about today, Jason's going to talk a little bit about staking. So we sort of group staking technologies that we have that are for integration, InfraStake and nanoSTAKE, in sort of one methodology. We have a whole business unit with integration support that's in that department. Then we've got our welding technologies, which are a little bit more custom, a little more tailored to your specific needs. I've already talked about what those are. And then we've got a tooling methodology that we think is pretty slick and that Jason will get to later on in the webinar here.
Yeah. Any questions so far about the difference between staking and welding? Why is 3D printing considered tooling? Anything like that? Before we jump in, because I'm going to start talking about InfraStake and nanoSTAKE and how those two staking technologies work. Jump in because
Cool. Roll on, Jason.
All right.
Sounds good.
So the InfraStake process, you could look at it as a 4-step process. You could also, the clamp and retract phase are up and down. So first we clamp. InfraStake is unique because the modules actually clamp the stake point directly at each location. The concentrator, that's the end of the module, is pushing on the two parts in your assembly to make sure that they are tight. They hold them tight, and the IR bulb turns on, and we heat the plastic boss. We do that using reflective geometries that focus the IR energy onto that plastic boss. That keeps the heat right where we want it. It doesn't go onto the mating surface or soak through to the lower part or anything. We just heat the plastic boss. And then we take our non-heated forming tool, we like to call it the punch, that comes down and forms that plastic boss into a stake head. And the blue lines in there, we're blowing cooling air to try to cool everything down quickly. And then once it's cooled sufficiently, we retract the punch, and then we can retract the entire module. So here's a quick video of how that works.
We're going to highlight these technologies, maybe 10%. So if you've got more specific questions or want to understand more deeply about what the technology we're talking about are, our website's got tons of webinars. We'll be happy to talk through those with you. This webinar is just specific to maybe how machine builders might utilize our technology. So, we're giving a 2 or 3 slide intro. We literally have pages and pages of information.
Yes.
Keep that in mind.
But if you want to know more about how it works, feel free to ask.
Yeah.
There's other videos. So when we're providing an InfraStake integration package, we also offer InfraStake software. This software is available to you. You download it and you would install it into either your Allen Bradley PLC system or your Siemens PLC system. And the InfraStake process then utilizes the machine PLC to do to control it. You don't have to come up with how to program all of this different steps of the InfraStake process. We have that available to you. So here. All right. So this is an integration layout. What's important here is that the areas that are in blue on the left hand and the right hand side, those indicate things that the integrator or the machine builder would need to provide. Those are not provided by Xtel. So on the left hand side, there's a couple different valves. There's 2 3-position solenoid valves. One is for the cooling air. One is for the punch air that allows us to do low pressure boss sensing. And then the other is a 2-position solenoid valve that controls the punch motion firing back and forth. On the right-hand side, we've got the machine PLC, and we've got a 24 power going into the module. The machine PLC communicates with the PM400 power supply that Xtel provides, and that is what powers the modules and controls that. And then there's a power converter that is going into the punch sensor, because on an InfraStake module, the punch sensor is measured at throughout the cycle. So we can actually measure how high it is and where it is in, is it forming the boss all the way? Is it touching off on the top of the boss? We can measure all of those positions. If you want to take a screenshot, you're welcome to do that. We also have this image available on our website. And so I can provide a link to that in the follow-up email after this webinar. Next is nanoSTAKE. So the nanoSTAKE process is different. InfraStake was using infrared radiation energy. nanoSTAKE uses conduction. First, in nanoSTAKE, what we do is we heat the punch up to a programmed melt temperature. And there's a sensor inside of the heater, so we know that we've actually achieved what we're telling it to do. So it heats up to a programmed melt temperature. It touches on the top of the boss and forms it slowly. And we measure that motion so that we can measure the final height of our stake. Once it reaches the final height, then we cool it by blowing cooling air through the module to a programmed release temperature. It's not a timed cooling phase. It's trying to target a certain temperature. And once we've hit that temperature, we retract the module. So I'm going to show the video on the left is a thermal image. You'll see that the thermal on one side and the actual on the other side. I want you to, since it must be hard to hear me through the video. So what I want you to notice is just the small tip that gets hot. The rest of the module stays cool, and it cools back down so that you can actually touch it at the end of the cycle. So that's another kind of interesting thing to note. nanoSTAKE stays at ambient temperature whenever it's not in use, which is different than like a hot punch would or other types of technologies. The one on the right is a more automated system. Did you notice the LED lights? They kind of change color at like different times. That's because every single nanoSTAKE module is independently controlled, and the LED light is indicating what is happening with the module. Red means it's hot. Blue means it's ready for the next cycle. I think they turned green right at the very end where it's saying, yep, we achieved everything. It's great. Looks like there's a question.
Yeah, Bill is asking, based on the boss geometry, the tip changes or the tip shape always the same? Usually they are custom per application. Usually, like is in the video that Jason just showed, they would be common within one machine.
Yeah. So we make sure that the punch cavity is specific to your application. But most part designs have a common boss design throughout that one part. Not always. And we would make sure every nanoSTAKE punch is suited for the plastic boss that it's going to stake. nanoSTAKE has an independent process controller. So rather than using the machine PLC to control the nanoSTAKE process, it has its own process controller that communicates with both the machine PLC and then it controls nanoSTAKE. This makes it a little more plug and play for integrators. That means you can just wire up the process controller and give it a go signal and wait for it to tell you that the process completed successfully. This is a breakdown of the nanoSTAKE integration package layout. So you can see the nanoSTAKE module there in the middle. Again, there's a few components that the machine builder needs to provide. So there's these items in blue. Again, it's valves that would be inside of the, your machine. And then the machine PLC has to just simply tell the nanoSTAKE controller to go and be done. The tool diameter is 8 and it stays the same for all various tip geometry.
I think it's 10.5 millimeters if I'm thinking right. So the module itself is actually it's either 10 or between 10 and 11 millimeters. Can do slightly larger than that, but there are some implications to that.
Yeah. So like if this is your punch here, this is roughly 10 millimeters in diameter. And then this punch, like most of the time we keep it smaller than the outside, but what Nick is saying is sometimes we make it a little bit wider.
Yeah. So, but nanoSTAKE we developed years ago because of size constraints to InfraStake. InfraStake's a great technology, but sometimes it just doesn't fit. We really developed nanoSTAKE for PCBs and lighting application. Some consumer products where the packaging is the constraint. So yeah, it's a good question. It's a bit size constrained, but that was really intentionally. It was part of the design.
Right. We wanted to be able to fit in small areas.
Yep.
All right. Next, we're going to talk about InfraGuide. You want to take over?
Yeah. Okay. Too. I guess before we move on to welding, any other questions on staking? No questions. Great. So we're going to move a little bit more to welding integration packages. Jason, should I take over?
Yeah, you can just hit take control.
Okay.
All right.
We're going to see how this goes.
I'm going to take it back. Just kidding.
Got it. A little later. Cool.
Yeah.
Great. So the InfraGuide process is it's an infrared non-contact welding technology that Xtol developed. We do other types of non-contact welding as well, but this is a little bit more integrator, machine builder friendly from an implementation standpoint. It's similar to hot plate welding. If you're familiar with that, it's a bit more common of a welding technology, we would say. You've got two plastic components. You're heating both components for a melt time, as we call it, through a process control. You get the heated tool out of the way, and that's an open time, open step of the process. And then under controlled pressure, you push everything together. So that's kind of a summary, a very simple summary of the technology. The key around InfraGuide is you have independent emitters. If you're a machine builder out there and you try to use different emitters, sometimes that can be a little tricky with respect to uniformity. And this technology has some benefits around focusing the energy instead of masking it, independent bulb control, so we really get incredibly uniform melt, things like that. So that's kind of the process in a nutshell. This is the InfraGuide product in your machine. Able to hear me. That what happened in that process there was, I'm going to play it again here in just a moment. You've got two parts, one an upper press, one in a lower press. the emitters come forward. There's a melt time, as Jason described during InfraStake, where you can actually see the infrared energy on. And those emitters get out of the way, parts come together, and there's like, I think, a 7-second seal time in this. So that's the process in a nutshell. We're going to talk about how that breaks out to integration here in just a moment. All right, so what would an integration module, if you approached Excel and said, hey, I've got the need to do some infrared welding? First thing is we would need to evaluate the CAD, make sure that it lays in properly. There are some geometry constraints with InfraGuide. Kind of see how with these tools, there's a bit of a radius that we have to be conscious of. But obviously, package would include the emitters, which include the bulbs, the assemblies that go with that, and the optically engineered surfaces, the pneumatic, plumbing, and manifold, all the pneumatics that go with that, the electrical wiring and the junction blocks, so that we've got a schematic that would say you need 24 volts at wiring that's appropriate for that, and then the power supplies, same power supplies we use for InfraStake, and a template PLC program, so you've got the kind of process control that you need.
Nick,
Jason?
are those just a mask?
They're not a mask.
Oh,
InfraGuide is guiding the energy. It's guiding the infrared energy. We put it in the name kind of on purpose. And so InfraWelding has had some challenges with respect to masks. Over the years, we've heard that masks can be less effective than what is required. You can kind of heat more of the parts than you need to. These have a very defined cool part of the part and melt parting part. Let's see. So, very focused energy is what you're going to get with it. Just for the sake of time, we're going to keep moving here. Through transmission laser plastic welding, the process is pretty, again, just sort of simplified version. It's a 3-step process where you are clamping the parts together. We turn a laser beam on, typically around 1 micron or 1,000 nanometers. We've got a lot of information out there on laser welding. So just briefly, I'll say that we're passing in this sort of direction. You can kind of see this darker part of the image is where the laser beam has gone, and then you have to cool it. The laser's transmitted through the part for true transmission, kind of in the name, but there's material requirements around the upper parts. They don't have to be clear like what's shown here, but there are material suppliers that will do an opaque material. And they do need to be well designed properly so that you can get the energy all the way through it. Yeah. So tons of more information out there, but again, to focus on the integration of these kinds of systems, we're going to show 2 more videos on this one as well. This first one is more of a standalone machine that you could use a pick and place to get in and out of. This particular customer was going to use an operator until they had volumes that required it. We'll go ahead and show the process here. Okay, this next one here, we're going to show, this video doesn't have parts with it. We've got some customer sort of confidentiality we're maintaining here. But this would be a system where we were providing just the dial assembly and welding. They heard in there.
I didn't notice any pew 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 sounds.
There's no pew pew pew. Unfortunately, we can add that if your customer wants that. So to try to sort of tidy all this up, where does Xtool stop and where does your equipment start? You saw sort of an image or the video of a standalone machine that was doing laser welding. It was actually doing laser marking. It had a reject. And then those parts would actually be conveyed out, pick and place in and out. So that particular customer wanted a pretty cut and dry, I would say, standalone machine. So that's certainly an option. These are really simple. I mean, these are about as straightforward as it gets from a proposal standpoint. There are other options, though. This is the option on the right here. You see is a much larger system that our customer has going. And you see this very independent system that is over top of that conveyor. In this case, this customer, we said, let's, from a validation standpoint, have more of a standalone interface or standalone machine that we could use the pallets and basically validate everything on our floor so it could drop in. Timing was really critical to this particular opportunity. And so we're going to do a fully validate, and then it should be a plug and play. We're machine builders. We know that's not usually the case, but moves this much further along. So a standalone machine, I should say that with laser welding, be very careful. You need to have a laser safety officer certified within your company. You need to submit to a federal agency and get a number assigned to that to make sure you've got proper risk assessments. These lasers can have some safety implications. So that's a part of the package as well. And then, as I showed the dial assembly, we can do various other sort of layouts. But these are sort of three examples for showing the scope of all of that sort of thing. We've also done laser systems where it's not necessarily automated per se, but the laser system was part of a bigger base, and there was other stuff going on the standalone machine. So that is laser welding in 5 minutes. Hot plate welding process, similar to InfraGuide, 2 components brought together, contact with a heated surface. The heated surface, or the parts get off of the heated surface. The heat plate gets out of the way, and then again, under controlled pressure, we press the parts together. So 2 videos to show you here briefly. This one on the left shows the process and one of our standard pieces of equipment. The one on the right shows more of an automated setup. And then we'll show a couple of other form factors as well for hot plate welding. So I will be quiet and let you guys watch the video since you can't hear me anyway. Chat about thermoplastic tape at a fairly high rate. I would say the kind of tape stuff that I personally have seen here requires usually a sort of primer to be applied. The tape have different, is it being manually applied or does it need to be applied on a roll? that one probably is a specific question we would need to probably go back and forth on a little bit more. I would say it's probably not a hot plate welding, or might even be a welding application. So, so let's stay tuned for that one. Let's come back to that. Good question. Those are the kind of questions we like. Fortunately, that might be a back and forth connection. The second one here uses the hot plate welding process. It required an ultra fast cycle time. I think we were running for hot plate welding anyway. I think the cycle time on this is like 13 seconds. 15 seconds. We'll go ahead and show this. Jason, is if this automated quick machine and you see a hand.
Yes.
Yeah. And I'm sure everyone caught that.
That's because it was at our facility.
That's right. So in this sort of situation, we can do various configurations with the welding equipment. If you're wanting to do the loading and unloading of that, that's really straightforward for us. We've got a variety of different pre-engineered packages, and then also we can customize that to your customer's need. So just one more thing on welding. Oh no, that's not true. We have spin welding here. Just a minute. So just again to show you the sort of scope and breadth of what we do with the mechanical solution for each technology. This particular solution on the left was a 6-up hot plate welding solution for a customer with through conveyor sort of package. So this is a pretty tight package, all self-contained. With the exception of the bottom, the lower part, which was on a through conveyor. So that's not shown here. You can see the 6 individual, these are the heat plates here. So the motion would bring the heat plates in. 6 independent force control actuators on the top. So each process was independent, even though it was a multi-cavity. A little more cost and complexity there, but that was the end customer's requirement. So oftentimes with hot plate welding, if you can commonize tools, that's great. Hot plate welding process is really beneficial to sort of melting away any imperfections or variations that you have. You can't really do that with non-contact. So this is one solution that we customized. We did run this off at our facility before we shipped it for factory acceptance. And then you can see our standard welders on the right. We've seen these implemented in automation with pick and places quite frequently. So definitely a solution for you there. I'm not going to go into it, but we've got a lot of different process control features, all kinds of things on the controls package of those machines. Spin welding, just real briefly, pretty simple process. It's a friction welding process. You're spinning one part. You need to hold the spinning stops abruptly, and then the parts are held together for a curing process. 2 videos. For this one,
I'm always blown away at how quick that is.
yeah, if you're watching this, you might be asking yourself, well, spin welding is really fast. Why don't you just do that all the time? It's because the parts need to be, the weld joint needs to be circular. So it's a little bit more of a niche welding technology, even though it's really fast, really simple, pretty cost effective. So if you're asking yourself, all right, I saw 2 standalone machines, how's that integration package? We had that product in the industry for probably 15 years, I think, Jason. And we found that in the last 5 years, our integration packages we would sell were substantially more than our standalone benchtop machines. So we developed this latest iteration of this. It's called the Vortex Eminence. And you can kind of see the level of documentation you get. I alluded to this earlier in the ease of integration. We want to make sure that as a machine builder, you're going to hand this to a controls engineer at some point, and they're going to say, what's my IO? What's my go signal? What's my stop signal? How do I get process parameters back? We go into pretty substantial detail on this particular solution for that. Mounting, calibration, all those things. We've done some updates with this particular wall platform. So,
Okay.
questions on welding? Oh, nope. Jason's got one more.
Well, this is still technically welding. So InfraWeld, you can ask your questions, by the way, anytime.
Yeah.
I'll stop talking if we get a question. InfraWeld is more of a module style welding solution. It was developed to put components on the back side of automotive headliners. It uses infrared energy. It focuses the infrared energy just like InfraStake, but it focuses it in a different spot. So here we are shining that infrared energy through a semi-transparent, something that's transmissive of IR component, and then that's being absorbed by the back side of a headliner. And then the module is sealed, so we can actually pump cooling air into the module and use that to pressurize the joint. And that pressure is what drives the components into each other. Rather than a physical tool that's pushing on it, we're using air pressure to push down. And then once that it is, pushed into place, and the parts are, starting to re-solidify, then we back the module away a little while and then blast cooling air at it to cool. It really is pretty slick. Then we're going to show, I forgot about the animation. Here is a video. It's fairly old, so I apologize for graining this. Like that. OEMs like that technology because it eliminates weight from the vehicle. It creates some space savings, and it's pretty efficient. This is an InfraWeld integration layout. It's very similar to the InfraStake one, but it doesn't have any punch measurement to have on it, so it's a little simpler. And then again, the areas in blue are things that the machine builder or the integrator would need to supply with their machine, and then everything else is stuff that Axle provides. Next, I want to talk about 3D printing. We kind of had that at the very, very beginning and talked about that. We see 3D printing as a really, really good solution for tooling. And some of the benefits are that you get dependable lead times. You can get 3D printed nesting blocks in 5 or 10 days rather than 4 to 6 weeks if you have to outsource your CNC cutting. You get design freedom. 3D printing, everybody knows that you can have more design flexibility. I'd
like to add just one quick thing, and then Jason. Yeah, one thing I've seen machine builders do is implement airlines in end-of-arm tools. If your end-of-arm tool is heavy and you need to lightweight it, is that bird?
Yes, lightweight it.
Lightweight it. Yeah. Reduce weight. It's a really slick way to approach that. We've seen it for clip driving and some other things where you implement sort of manifolds right in the tool itself. Yeah. So you can lightweight end-of-arm tools, which can be, that can be a big cost driver if you've got to upsize your robots for big heavy tool weight.
Yeah. with 3D printing, design complexity is free. So features that you can print into the detail, the better. We have soft touch and non-marking materials. So in applications where it's sensitive A surfaces, maybe it's painted or glossy or something, and you really, really need to be delicate with that. This can replace the need for moleskin or machined Delrin or poured cast urethane. You can 3D print your nesting and it's safe to use. We call it soft touch tooling. Basically, you have a TPU material that we're printing, and that's what's contacting the surface. We've used this in assembly fixtures, end-of-arm tooling. There's some instances of it where it's a total block that is 3D printed in that one material. In other cases where you only really need the TPU on the part that's contacting your assembly. So we just do TPU on the very top, and then we have a riser that's out of a different material that's maybe more stiff, so that you don't have to worry about it flexing, anything like that. So this one's a printed nylon. We've done it with aluminum bases. This one here, it's TPU on the top, and then it's got some hex risers on it. There's a lot of different options and possibilities there, but it turns out to be a really, really good solution. One of the biggest questions that we get is it strong? It's 3D. Isn't it weak? But it's not weak, and you'll be able to see that in this video. That's kind of fun. Is it? So I think it's safe to say that it held up.
Yeah. Shout out to Andrew who's on the webinar here. And then also this was one of our designers and machine builders who built that. Was quite proud to case this blazer in a video.
It did.
Yes. It is lit.
Yes, thank you. So that is a very quick overview of all of the different plastic assembly technologies that you can utilize and implement into your custom automation. Questions?
Yeah, Jason, we have one from Aaron here who's asking for optimal plastics, compositions, properties. Great question. Actually, I've never heard it sort of asked this way. This is kind of, I don't know if we have two tools that we should probably highlight, maybe send out as a follow-up, Jason. Mm-hmm. We have a, what is that one, Doc?
The plastic decision matrix?
We have a plastic decision matrix, which sort of talks super high level, right? Like we've got application engineers that want to go as deep as you'll let us, as you want us to, around the particular weld geometry, form and function, plastic material, all those things together. However, if you just want a ballpark idea, we've got a tool that we're going to use that helps to sort of say, do you need a hermetic seal? Is it really high show surface? Does splash dust matter? All those things matter when selecting a weld technology. There's other weld technologies we did not mention in this webinar, like vibration welding and ultrasonics. But that's because those are sort of outside of the integration space for Excel. And those are also part of that conversation. So the other thing I would say, the second tool is we do have compatibility charts. Not all plastic needs the same plastic to weld together. There's sort of a family around polycarbonates, ABSs, PMMAs, all those sort of weld in various strengths and whatnot. So we'll do a follow-up with those two things, but those I think are more weld technology specific. I'm wondering if Aaron has more of you have sort of all technologies. See, this is,
boom.
You guys, if you don't know Jason Dornbos, this is what you get right here.
This is the plastic welding decision matrix that Nick was just talking about. And I'll send a copy of this along in the follow-up. I'll send a copy.
Or probably half of you took screenshots.
Yeah, you can take screenshots. That's fine too. You can also go to the website and there's a download button for it.
Any other question?
If you have anything else that comes up, anything else that you think of, feel free to just respond to the follow-up email that you receive, or you can, if you happen to know our email addresses, you can simply just send us a note or give us a call, and we'd be happy to help you out. Thanks everybody for joining us. Have a great rest of your day.